Hello and welcome to section 4 in our journey to learn Go. In the previous section, we covered some powerful key features of the Go language, like concurrency, handling errors, and slice tricks. Now that we have the knowledge to build medium complexity level programs in Go, it's time to dive into advanced topics. In this section, we will take a closer look at interfaces and methods in the Go language, covering advanced features of both interfaces and methods. We will then move into advanced OOP concepts, or object-oriented programming concepts, like the factory pattern, the singleton pattern, and the builder pattern. We will also build a piece of the Hydra software with each one of the object-oriented patterns that we will be covering in this section. Now we move to the first video of section 4, where we will explore more advanced features of methods and interfaces in Go. Due to the depth of the subject, we'll cover it in 2 videos. Welcome to the first one. In this video, we are going to dig deeper into interface conversions and tricks to consider. We'll then conclude with discussing the empty interface. Let's start by digging deeper into interface conversions in Go. Going back to the node interface example we did in video 3.2, as a refresher, the node interface contained only 2 methods: setValue, which takes a value as an argument, then sets it in the node, and getValue, which gets the value of the node. The node interface served as the parent interface for 2 struct types: the SLL node struct and the power node struct. The SLL node type acted as a normal node in a single linked list, where each node stores a value as well as a pointer to the next node. In the SLL node struct, we'll add a new string field called SNodeMessage to represent the unique field that only exists in the SLL node type. In the constructor for SLL node, we will change the previous code from video 3.2 to use a struct literal to initialize the struct, the SLL node struct, with a string message in the SNodeMessage field. As a reminder, we call the argument between the func keyword and the function name the receiver. A receiver represents the type which implements the method. So if we think from an object-oriented point of view, this is our object type or our class type, and this is the method that our object implements. The power node type was similar to the SLL node type, except that it multiplies any value it receives by 10. In the power node struct, we'll add a new string field called pNodeMessage that is unique to the struct type. In the constructor for the power node, we will assign a string message to the power node pNodeMessage field using the struct literal notion as before. Now let's write a function that would simulate a node getting created. For starters, we'll create a new SLL node, then we'll set the value as a value given to the createNode function, and because SLL node implements a node interface, we can simply return it as a node interface, as shown. So this becomes valid code. Let's explore a feature of Go called type switch. By using a type switch, we can test the type of a certain value from multiple choices. The syntax is to use dot with the word type between round brackets next to the interface value that we would like to inspect in a switch statement. We assign the concrete result of the conversion to another variable. In the code here, we use a variable called concrete n to store the concrete value produced from the conversion. The two cases here in the switch statement represent concrete types that we check against. Since n is of type node, since it's a result of create node, then that means that n could either be a pointer to SLL node or a pointer to power node. That is because those two types are the two types that implement the node interface, which is why the two cases in our switch statement check against those types. Because create node in this case created a node type of SLL node, this case will be the one evoked with this code. We verify that the concrete type is what we retrieved from this statement by calling a field that only exists in this particular concrete type. So as we have done earlier, the snode message only exists in SLL node. It does not exist in the power node type. So I copied the code over to play.golang.org so that we can test it quickly. So if I just hit run, we'll see here that we got this message, and also we got the special message we stored in the unique field, the snode message field, that only exists in the SLL node type. Perfect. So that proves that using the switch types, we were able to retrieve the full concrete type that was being represented by the high-level interface. If we create a power node instead, we'll trigger the second case, as shown. Notice how returning the power node still satisfies the create node function. Again, that is because the power node implements the node interface. Let's cover some important gotchas when working with interfaces. Gotchas represent tricks and common mistakes when dealing with interfaces. In Go, when the type implementing the interface method is a pointer, only a value of a pointer type can access these methods. So for example, if we create a node that is just a straight SLL node struct and not a pointer to that struct, we would not be able to assign this value to the interface because n is of type node, and node is only implemented by the pointer to SLL node, not a straight value of SLL node. So as seen here, the type that implements the interface methods, the node interface methods, is a pointer to SLL node. Which is why this code produced this error. And it states clearly the reason for the error. To fix the code, we will make snode a pointer to SLL node by using the end symbol, which would indicate that this is an address for an SLL node struct, hence a pointer. If we run now, we have no more errors. It works as expected, and n accepted snode. This functionality is by design in order to protect the coder from invoking a pointer receiver without needing so. That is because a pointer receiver can change the values that it points to. So in other words, when we say here, for example, snode.value equals v, we actually change the value in snode. Whereas if that was not a pointer, this would have been a copy of snode, and it would not have changed the value of the original snode. So go make sure you're certain in using a pointer to make your calls. The reverse of this rule is valid in Go though, meaning that if we have a type that implements methods of interface type I, then a value of either the type or a pointer to that type can access those methods. Let's see what that means by writing some code. Instead of having the method receiver as type pointer to SLL node, we'll have it as type SLL node directly. So we'll remove the pointer references and the address reference here. So now the SLL node type is the one that implements the node interface. In the create node, I put back new SLL node and doesn't return a pointer anymore. So if we look at this code here, even though snode of type pointer to SLL node with value of 15, we can still access the methods of type SLL node, which is not a pointer as shown. So this is permitted, and Go will take care of the indirection for you. So if I hit run, you can see here that the snode.getValue printed the value of 15. So we accessed the method. Perfect. That's the second trick with interfaces in Go. A third important gotcha is that the receiver of a method can be nil without crashing the application, which is unlike other languages. Let's demonstrate that with an example. We'll handle the case if a receiver is nil and return an error to let the caller know it needs to initialize the receiver. So let's create an error called error invalid mode, which is an error representation of the invalid code. Next, in the setValue method, we can also put those back as pointers. So now we're back to having the SLL node pointer type implementing the node interface. Next, in the setValue method, we can actually add a Nil Check. So we can actually do something like this, and this is valid code. So let's change our main function code to test out this. So we'll create a variable called SLL node of type pointer to the SLL node struct. This pointer is not initialized because we do not assign any value to it. When a pointer is not initialized, its zero value is nil. which is equivalent to null in other languages. So that means when we call a method straight from that nil pointer, this code path will be followed. So instead of a panic, Go will still execute the method and it will get to this point. So in this case, our code detects that this is nil and it returns an error. So when we hit run, we see the error here. The invalid node error. Perfect. This is a powerful feature in Go because instead of checking whether this value is nil outside whenever we need to call a method on it, we can simply put the check inside the method itself, and that will take care of the validation. Perfect. An important note is that if we try, on the other hand, to do something like this, where we call a method directly from the interface type, as shown, a panic will occur because the interface value has to be assigned. So if we change the code to look like this, so we assign an address of the SLL node struct to n, meaning that n will host a pointer to the SLL node type, the code will work. The reason why it outputs nil is because said value returns an error, and there was no error. So hence, that's why the return result was nil, meaning that it was successful. No crash. So let's write new code to showcase the power of the empty interface. We will write a function called print type that takes an empty interface argument. And that is the syntax for the empty interface. The word interface with 2 curly brackets. So our argument is called I. We inspect the types of that interface using the switch type statement that we have learned earlier. And then we print the type that we find. So if we use this function with different argument types, so this is a string, this is an integer, and this is a float, then hit run, it works. As you can see, we can push any type to this function, and Go didn't complain. That is because any type out there is a child of the empty interface. We were also able to control the behavior of our code based on the data type that was received using the switch type statement. This shows a very powerful side in Go, which makes your code very flexible. This is key when designing generic APIs. So how come we printed string case and int case as shown here, but not the float case? It's simply because the default float in Go is a float 64 type. So if I hit run now, you can see that the float type now prints as well. Perfect. Let's showcase another example of the power of the empty interface. We'll create a struct called magic store, which can store a value of any type by having a field called value of type empty interface. We'll add another field called name in case the user of the struct would like to name the instance they are using. So just to give a name to the magic store. We will get the magic store pointer to implement 2 functions. SetValue and get value. Lastly, we'll create a constructor called newMagicStore, which will take a string and it will return a pointer to the MagicStore struct. Inside our constructor, we will create a new pointer to MagicStore and we will assign the name property of the struct with a value that is passed as an argument to the constructor, which is the name we would like to give to the MagicStore. Now let's write some code in the main function to store and retrieve the value from the MagicStore struct. We'll start by creating a new MagicStore. We will call it integerStore. We will store that value in a variable called iStore. We'll then set the value to 4 on that store. So 4 is an integer, so we stored an integer value. We will then use the type assertion from the value stored in our MagicStore to retrieve the value stored inside the MagicStore. To prove that this is a normal integer, we'll multiply it by 4, and then we'll print the results. Next, we'll create another MagicStore. This time we'll call it the stringStore. We'll store it in a variable called sStore. We'll set the value as hello, and then we'll use type assertion to get the value stored in that store. And to prove it's a normal string, we'll concatenate it by another string, which would be space world, and we'll print the results. So if I hit run, this code works. So our MagicStore is really magical. It was able to store an integer and a string. And we were also able to retrieve those values and use them natively. This shows us another example into how much Go can be flexible when writing code using the empty interface. However, like any other powerful feature, we need to be careful not to overuse the empty interface. Sometimes it will make more sense to tie the code to the expected types. In other times, like building a generic API, we will need the empty interface. This video served as a closer look into advanced features in the Go language, which provides the ability for object-oriented design. This video is rich with code examples to solidify the powerful concepts.